scientific process as a unifying thread to make connections in chemistry. In part 1, we discussed in detail major activity 1 of the scientific process, namely gaining or accumulating isolated facts about nature, and also the first tool used in major activity 2A, namely comparing and contrasting the gained isolated facts in order to generalize or organize them. In this part, we will look in detail into the second tool used in major activity 2A as well as into major activity 2B. The second tool used for generalizing or organizing facts is looking for and recognizing the existence of mathematical patterns in a set of related quantitative facts, namely numerical experimental data. The numerical pattern so discovered simply indicates that nature follows a corresponding rule in its behavior. The rule is referred to as a law of nature. The numerical pattern expressed in the form of a mathematical equation constitutes the mathematical statement of the law. The implication of the mathematical pattern is in turn expressed in the form of a verbal statement of the law. As an example, let us analyze the 5 trials of data for the combining masses of hydrogen and oxygen to produce the masses of water shown in the table. We recognize a very simple numerical pattern involving the numbers in a given trial that is common to all 5 trials. This table shows that pattern. The mass of water produced is the sum of the combining masses of the 2 elements within experimental uncertainty. This pattern is observed in all trials of data for this reaction as well as for any other reaction, no matter how many reactants and products are involved. This indicates that nature follows a rule in its behavior with respect to all chemical reactions. Science refers to such a rule, as mentioned before, as a law of nature. The above pattern and hence the rule were discovered by Antoine Lavoisier in 1789 through his various experiments, specifically an experiment that is popularly known today as 12-day experiment. He heated liquid mercury in a flask, exposed it to air for 12 consecutive days and nights to ensure that the reaction was complete, and then measured the combining masses of mercury and oxygen as well as the mass of mercury 2 oxide solid produced. He wrote, "One may take it for granted that in every reaction there is an equal quantity of matter before and after the operation. This law is called the law of conservation of mass or matter, implying that mass or matter is neither created from nothing nor destroyed into nothing in any chemical reaction. The mathematical statement which expresses the numerical pattern recognized in the data is sum of the masses of the products formed is equal to the sum of the masses of the reactants that react together. It is important to keep in mind that it is not the sum of the masses of the reactants taken for the reaction, but that of the masses which react together. The actual algebraic equation depends on the actual reaction in question. For the example just considered, it is mass of H2O equals mass of H2 plus mass of O2, with the implication that MH2 and MO2 are the combining masses. One can also recognize another numerical pattern hidden in the same data as seen in this table, which is recognized in the data of all the trials of experiment using this reaction. The ratio of the combining masses of hydrogen and oxygen, as shown in the last column, is always the same within experimental uncertainty, no matter how much of the two gases actually react. The average of these 5 ratios happens to be 1.00 to 7.91. With the help of sophisticated instruments, the ratio is found to be 1.00000 to 7.93668, the average ratio above for the limited data being close to this more precise ratio. This implies that all different amounts of water always have the same fixed composition, namely for every 1.00000 part of hydrogen, there are always 7.93668 parts of oxygen by mass. The same pattern is found to exist in the case of a vast majority of compounds, though not all. Nature is again seen to obey a rule. Some examples of compounds that do not obey the above rule are the oxides of zinc, iron 2, and tungsten. These are called non-stoichiometric compounds or Berthollides, and the ones that do obey are stoichiometric compounds or Daltonides. Recall that a ratio in the form something to something else can also be expressed in the corresponding fractional form. Therefore, an alternative way to express the above pattern is shown in this table. Thus, it is noticed that mass of O2 over mass of H2 reacted together is a constant within experimental uncertainty for all the trials. This implies that for all the trials, mass of H2 over mass of O2 reacted together is also a constant that is simply the reciprocal of the previous constant. The corresponding law is called the law of constant composition of compounds, whose mathematical statement is mass of element 1 in a given sample of a compound divided by mass of element 2 in that same sample is a constant. The verbal statement is that different samples of any given Daltonide contain its constituent elements in the same fixed composition by mass. The law of constant composition was discovered by Joseph Proust in 1794. He prepared copper 2 carbonate in the lab and showed that it had the same composition by mass of copper, carbon and oxygen as the naturally occurring compound. He also studied each of the two tin oxides, namely tin 2 oxide and tin 4 oxide, as well as each of the two iron sulfides, namely iron 2 sulfide and iron 3 sulfide. He demonstrated that different samples of each of these compounds had the same fixed composition of the two elements in question. In 1799, he showed that the sugar in grapes is identical to that found in honey, and both had the same composition of the component elements carbon, hydrogen and oxygen. What a marvelous order had Proust found in nature. He said, "The stones and soil beneath our feet and the ponderable mountains are not mere confused masses of matter. They are pervaded through their innermost constitution by the harmony of numbers." Johannes Kepler, Galileo, and Isaac Newton regarded nature as mathematical. Proust added a chemical testimony to it. However, a distinguished French chemist, Claude Bethune, personal instructor of chemistry to Napoleon, along with Franz Wald and Wilhelm Oswald, strongly insisted that the composition of chemical compounds varied depending on the manner of their preparation. This is the reason why non-stoichiometric compounds are called Berthollides. Many other chemists did not support Proust in favor of Bethune. Proust used the purest of chemicals and the most accurate apparatus possible. He repeated the experiments of Bethune several times. He took every precaution to avoid error and found mistakes in Bethune's determinations. In addition, Bethune had used glass and alloys, which are not even compounds but mixtures, as well as mixtures of various liquids. Nevertheless, for 8 years, Proust had to try to persuade the scientific world, especially Bethune and his followers. Eventually, Bethune realized his mistakes and graciously withdrew his arguments. Fortunately, around that time, Jan Berzelius happened to be a giant of an experiment experimenter. He discovered several new elements and synthesized a large number of yet unknown compounds. He measured the combining masses of elements as accurately as the new apparatus carefully designed by him would permit. During this time of toil, holidays, distractions, hobbies, even food meant very little to him. His was an indomitable spirit. In 1818, he published a table which included the chemical composition of nearly 2000 inorganic compounds. The law of constant composition of compounds got established in chemistry. When one learns the history of chemistry, one would find several instances of how the scientific process develops in reality. Incidentally, the law of constant composition is just a special case of a more generic law called the law of definite proportions, a fundamental law at the heart of chemistry. It was discovered by Jeremiah Benjamin Richter, who coined the term stoichiometry, an important special term in chemistry that is widely used today. This law is applicable to any reaction, including reactions in which elements combine together to form compounds. Consider the generic reaction A plus B plus etc. gives P plus Q plus etc. An analysis of the corresponding experimental data reveals that a definite proportion, that is, a unique specific proportion, exists between the masses of any two reactants, of any two products, and of any one reactant and any one product. Thus, for example, mass of A reacted over mass of B reacted equals a definite constant K1. In other words, in all the trials, the ratios of masses of A and B reacted are equal to one another, and hence a proportion exists between these two masses. Recall that proportion simply means equality of ratios. Similarly, mass of P produced over mass of Q formed equals another definite constant K2. Mass of A reacted over mass of P produced equals yet another definite constant K3, and so on. Thus, according to the law of definite proportions, in the specific reaction we considered above, namely 2H2 plus O2 gives 2H2O, mass of H2 reacted over mass of O2 reacted equals K1, as seen earlier under the law of constant composition. Mass of H2O formed over mass of H2 reacted equals K2, and mass of H2O produced over mass of O2 reacted equals K3. One can verify the above using the data of the 5-trial experiment for the above reaction shown earlier to illustrate the law of constant composition of compounds, and again reproduced here. The average value of K2 is 8.90 for the 5 trials, and that of K3 is 1.10. 0.13. A much more precise value of K2 is 8.9366 and that of K3 is 1.12600. The whole collection of isolated facts and generalized facts, namely empirical classifications and laws, constitutes the first of the two major types of scientific knowledge, namely empirical knowledge. Empirical means pertaining to observation. Speculation does not come into picture here. We will refer to the second major type of scientific knowledge after we discuss the third major activity in the scientific process or scientific method. As we will continue to see in this video series, there are several widely prevalent misconceptions that are taught regarding the scientific process or scientific method. One of these is that scientific laws are absolute, meaning they have no exceptions at all. No. In addition to the law of constant composition of compounds, for which Berthollides make up the exceptions, as mentioned earlier, there are other laws that do have exceptions. A popular example is the ideal gas law, which is obeyed by real gases only under low enough pressures and high enough temperatures. Thus, the behaviors of real gases at high enough pressures and low enough temperatures are the exceptions to this law. What is enough depends on what the gas is. That a law has exceptions does not disqualify it, since it is evident that the pattern and hence the rule recognized is still true with respect to that part of nature which obeys the rule. Therefore, while learning any law of nature, it is important that the student always pays attention to its scope as well as its limitations and use it only where it is applicable. Thus, the law of constant composition of compounds should not be applied to Berthollides. The ideal gas law should not be applied to real gases under high enough pressures and low enough temperatures. Other laws that are taught in chemistry are listed here. As can be seen, there are several of them. Thus, one should realize that nature happens to follow several rules in its behavior, which we have recognized to exist in nature through our experimental data. A detailed analysis of experimental data plays an important role in science. A great example is the analysis by Clausius that led to his mathematical statement of the second law of thermodynamics in terms of entropy, which he felt forced to postulate to exist in nature while analyzing the data. Watch part 3 of my video series on entropy for the details of an example analysis. So, what is the nature of nature? As Phil Gibbs said in his essay on theory of theories, one thing is clear: nature uses mathematics. If this were not the case, if Nature was governed instead by a committee of demons who made nature follow their whims and fancies, then there would be little hope for us to understand nature and predict the outcome of experiments or invent new technology. Scientists would then be replaced by sorcerers. For the verbal and mathematical statements of each of these laws, and more importantly for the corresponding sample experimental data in which the numerical patterns were recognized, see my book Understanding Chemistry. There is an important advantage to discovering any law of nature. It can help us save energy, money, and time by allowing us not to do the corresponding experiment. How? After the discovery of a given law, experiments can thereafter be conveniently replaced by calculations. The tool used for this major activity 2b is to use the mathematical equation of the given law that contains a given number of variables in it. Knowing the values for all of them but one can solve the equation for that one unknown. While doing so, one should always make sure that the law in question is indeed applicable to the context considered for the calculation. This is an important activity in science, but more so in the classroom setup. Every student should realize the importance of understanding the chemistry concepts first and then seeing where and how math comes into picture as an essential tool in major activity 2b. Paying attention only to numerical problems should definitely be avoided by every student. Of course, teachers and professors also should accordingly help the students by explaining thoroughly the chemistry concepts first and then showing how math comes into picture as an essential tool. In other words, it is important not to convert the chemistry course into another math course. As an example of major activity 2b, namely predicting experimental data with the help of a given law, let us say one wants to know how many grams of O2 would react with 125 grams of H2 to form water and the mass of water formed thereby. According to the law of constant composition, mass of oxygen divided by mass of hydrogen in any sample of water is a constant, or mass of oxygen to mass of hydrogen is a constant ratio. In order to know the value of that constant or that ratio, we have to know one particular pair of combining masses of O2 and H2 that would produce the corresponding sample of water. Let us say we know that 16.00 gram O2 combines with 2.016 gram H2 to form 18.016 gram sample of water. The two ratios, namely the ratio of X to 125 that contains the unknown and the known ratio of 16.00 to 2.016 are equal. That is, gram O2 and gram H2 form a proportion. Applying the method of proportions, x over 125 equals 16.00 over 2.016. Therefore, cross multiplication yields 2.016x equals 125 times 16.00. Isolating x by taking 2.016 to the other side yields 125 gram H2 times 16.00 gram O2 over 2.016 gram H2. Gram H2 gets cancelled, leaving gram O2. On simplification, one obtains 992 gram O2. Whenever a proportion exists between any two quantities, the last step seen here is always of this particular pattern. Therefore, omitting the previous steps, this last step alone is what is used by chemists under the name factor label method as an efficient shortcut for the proportions method. In this setup, 125 gram H2 is called the given info in which the unit has to be changed. The one known ratio, namely 16.00 gram O2 to 2.016 gram H2 written in the fractional form, is called the conversion factor, since it helps the conversion of units and always multiplies the given info as a factor does. Thus, the simplest generic setup of the factor label method is given info times conversion factor equals desired info. It is well known to teachers and professors of chemistry that a number of students feel intimidated by this kind of calculation that they ought to do on several occasions in chemistry. It will be very helpful if they understand that factor label method is nothing but the last step of the proportions method that they were exposed to in a much lower level of math class. Notice that a ratio can be written in two ways, namely in the above case 16.00 gram O2 to 2.016 gram H2, or it can also be written as 2.016 gram H2 to 16.00 gram O2. Therefore, from any known ratio, one can always construct two possible conversion factors. In this case, 16.00 gram O2 over 2.016 gram H2 and also 2.016 gram H2 over 16.00 gram O2. Which one is valid in the given setup is simply determined by using dimensional analysis, that is, proper cancellation of units. The former was used in the above problem, where the given info was a particular gram H2. The later is used if the given info is some specific gram O2. Thus, while applying the law of constant composition for any two combining elements, we just need one known ratio to be used as the conversion factor matter. Interestingly enough, it so happens that we don't need to look for any literature containing the experimental data. One can extract the known ratio whenever needed thanks to Avogadro's theory and the resulting mole concept by making use of the atomic masses embedded in the periodic table of elements and the concept of balanced equation resulting from atomic theory. The student has just to learn how to extract that information from the periodic table and the corresponding balanced equation. In fact, the combining masses of O2 and H2 to produce water, namely 16.00 grams and 2.016 grams respectively, used in the above calculation as the known ratio, were extracted from the periodic table and the balanced equation. 2H2 plus O2 gives 2H2O. The power of the factor label method is that one can have a series of any number of conversion factors in order to keep cancelling the units. In contrast, imagine the tediousness of using the proportions method at every consecutive stage of converting units. The factor label method setup is simply given info times conversion factor 1 times conversion factor 2, etc. equals desired info. In some textbooks and hence by some teachers and professors, the factor label method is wrongly referred to as dimensional analysis. The dimensional analysis is only one part of this method when the cancellation of units is performed. The actual setup, namely given info times conversion factor 1 times conversion factor 2, etc., should correctly be referred to as the factor label method. We can apply the law of conservation of mass to answer the second part of the above question. According to this law, gram H2 reacted plus gram O2 reacted equals gram H2O produced. Therefore, 125 gram H2 plus 992 gram O2 gives 1117 gram H2O, which is the mass of H2O produced. As an alternative method, one can apply the law of definite proportions using the mass of H2 given in the problem as the given info of the factor label method and the known ratio of 2.016 gram H2 to 18.016 gram H2O obtained using the periodic table and the balanced equation. Thus, thanks to the three laws of chemical combination, namely the laws of constant composition of compounds, of definite proportions, and of conservation of mass, without doing any new experiment, we are able to save our time, money, and energy and predict the results of the corresponding experiment. This is the power of major activity 2B. Major activity 3 of the scientific process, namely making sense of, understanding, explaining empirical knowledge as well as predicting it, uses 8 tools in total. In part 3, we discuss in detail the first 4 tools, and in part 4, the last 4 tools of this major activity, which plays, as we will see, a very significant role in the process of science.